This is a pre-built version of the application. So let's go ahead and run it and do all the operations that we need here, and then go over what just happened. Now this is the equation of an elliptic curve over prime fields. So we perform all operations in mode P, where P is prime. And we want the values of x and y that would result in this equation being satisfied. So for x is equal to 0, we end up with this result, and we have the same result here and here. So we end up with those 2 points satisfying the equation. And for x is equal to 3, we end up with this result, and we have the same result here and here. So we also end up with those 2 points satisfying the equation. So we end up with 19 points that satisfy this equation, including the point at infinity, O. And we have a theorem that says that if we have a finite cyclic group with prime order, then all elements, meaning all points in this case in that group, are generators of that group, meaning all those points are primitive elements. So if we pick any point here, it will end up generating the entire group, and we picked this point 5 1, and it ended up generating the entire group 3 times. So each column here is the entire group being generated. So here we did 57 hops, and we can see the cyclic behavior. So 5 1 is repeated here and here, and 6 3 is repeated here and here, etc. Now if we have a huge number of points in the cyclic group, then we would not be able to do this, since it will take forever with slow hopping. So here we did fast hopping using the double and add algorithm, and we'll quickly go over how this works while writing and test running the application. So here we are doing 13 hops, and we ended up at this point, and this is generator point G, and D is the number of hops. And we'll also go over what this means while writing and test running the application. Now, before proceeding with the code, let's do a quick introduction. So this is Weierstrass equation of elliptic curve E over field F, and we will be using this reduced form of that equation. So y squared is equal to x cubed plus ax plus b. And initially we will use f as the field of real numbers, and then to do cryptography we will use f as the field of integers in mode p. Now those two curves are singular, so we don't want to use a singular curve, and a singular curve is when the discriminant delta is 0, like here, so the value of this is equal to 0, and a singular curve has repeated roots, so we want to use an elliptic curve with distinct roots, like those two, this one and this one. Now looking at elliptic curves, we can make the following observations: that an elliptic curve will always be symmetric about the x-axis. So if x and y, so the coordinates of p here, x and y, satisfy y squared is equal to x cubed plus ax plus b, then the coordinates of minus p, which are x and minus y, satisfy the same equation. And also we can observe that non-vertical, non-tangent line will always intersect the curve in 3 places, meaning given 2 points on the curve, P and Q, we can construct a third point. And we can also observe that non-vertical tangent line will always intersect the curve in a second place, meaning given 1 point on the curve, P here, and a tangent line at that point, we can construct this second point. And we can also observe that the vertical line will never intersect the curve in 3 places. This means that we can potentially take advantage of that fact in defining a neutral element. Now we take advantage of our first and our second observations. So the symmetry about the x-axis and the non-vertical, non-tangent line always intersecting the curve in 3 places. So starting from 2 points on the curve, we can generate many points. So given 2 distinct points on the curve and a line joining them, let x0, y0 be the third intersection point of the curve with the line. Now addition of 2 points is defined as p plus q, which is x0 minus y0. And we also take advantage of our first and our third observation. So the symmetry about the x-axis and the non-vertical tangent line always intersecting the curve in a second place. So this means that starting from 1 point on the curve, we can generate many points on that curve. This is 2p. So given point P is any point on the curve with tangent line to the curve at P, let x0, y0 be the intersection point of the curve with the line. We define point doubling as P plus P is equal to 2P is equal to x0 minus y0. And we also take advantage of our fourth observation, that a vertical line will never intersect the curve in 3 places. So we define a neutral element O as an abstract point at infinity. So O is visualized as located towards plus infinity or minus infinity along the y-axis. And we also take advantage of our first and our fourth observation, and the fact that minus p is the inverse of any group element p. So this means that p plus minus p is equal to O. Now those are the equations for elliptic curve point addition and elliptic curve point doubling, and we derived those equations in a previous video a while back. So we want to add 2 points P and Q with coordinates x1, y1 and x2, y2. So we end up with point R with coordinates xr, yr, where xr is equal to x3 and yr is equal to minus y3. And x3, y3 is the third intersection point of the curve with the line joining P and Q. And here in the case of point doubling, we have that P and Q are the same point, so x1, y1 and x2, y2 are the same, and we have x3, y3 as the second intersection point. So 2p is equal to r with coordinates xr, yr, and xr is equal to x3 and yr is equal to minus y3. So the equations for xr and yr are the same for point addition and point doubling, and s is slope, so it's equal to y2 minus y1 over x2 minus x1 for point addition, and for point doubling, s is equal to 3x1 squared plus a over 2y1, and s here is the slope of the tangent line through p x1 y1. Now a group is a set with one operation and a corresponding inverse operation. Now if the operation is addition, then the corresponding inverse operation is subtraction, and if the operation is multiplication, then the corresponding inverse operation is division, meaning multiplication with an inverse element. Now in order to have all four arithmetic operations, meaning addition, subtraction, multiplication, and division in one place, we need a field, meaning a set with an addition group and a multiplication group. So a field F is a set of elements such that all elements of F form an addition group with plus as the group operations and 0 as a neutral element, and all elements of F except 0 form a multiplication group with this as a group operation and 1 as the neutral element. And when mixing both group operations, the distributive law does hold, meaning A times B plus C is equal to A times B plus A times C for all A, B, C in F. Now suppose that G is a set of points on E, including the point at infinity, and E is any elliptic curve defined over any field F. So for all points A, B, and C in G, the group operation is closed, meaning A plus B is equal to C, and all 3 points are in G. And the group operation is associative, so A plus B plus C is equal to A plus B plus C. And we prove it here. So A plus B plus C, so if we take B plus C here, take this intersection point and we go down, so this is B plus C, and then A plus B plus C, take this intersection point and we go up here, so this is A plus B plus C, and here A plus B plus C, so A plus B, this is the third intersection point, and we go down here, we get A plus B, and then A plus B plus C is this intersection point, and we come up here, we end up with A plus B plus C, and those 2 points are the same. And there is a group identity element, A plus O is equal to A is equal to O plus A, and for all points A in G, there exists minus A in G, called the inverse of A, where A plus minus A is equal to O is equal to minus A plus A, and the group operation is commutative, So A plus B is equal to B plus A, and G, meaning the set of points on E, including the point at infinity, form an abelian group. Now to do cryptography, we need to use a curve over a finite field, for example prime field, where all arithmetic is performed in mode prime number p. So an elliptic curve over zp, where p is bigger than 3, is the set of all pairs x, y in zp such that y squared is congruent to x cubed plus ax plus b in mode p, and a and b are in zp, and O is an imaginary point at infinity, and this equation is different than 0 in mode P. So we end up with those equations for elliptic curve point addition and point doubling. And now we have mode P here, which we did not have when we were over real numbers. Now the source code will be available for download. Also a longer version will be available for watching by channel members at all levels, and it will include the coding and test running of the coded application.